So if we rewind, just a bit, in May of 2026, there was this fundamental shift in the U.S. energy grid. And it's one of those milestones that, frankly, 20 years ago would have gotten you laughed out of most utility boardrooms.
Oh, for sure.
Right. Because for the first time in history, solar power actually generated more electricity than coal. And it wasn't just like a brief afternoon spike when the sun was really bright.
Right, not a blip.
No, a sustained structural transition in how baseload power is interacting with, variable generation.
It is a staggering data point when you contextualize it. I mean, if we look back exactly 2 decades to the release of the documentary, An Inconvenient Truth, back in 2006, the projections for renewable energy scaling were, well, they were considered highly optimistic by critics.
Some called them entirely theoretical.
Yeah, completely theoretical. Yet here we are. And, analyzing the atmosphere really requires this kind of extended timeline. You have to sort of step back from the 5-day deterministic forecast and look at the decadal trends to understand the physical realities of the climate system we are currently living in.
Welcome to Meteorology Matters, the podcast that dives deep into the science, chaos, and stories behind the weather that shapes our world. This show was created by meteorologist Rob Jones.
And our scope today, for you listening, is entirely focused on the empirical evidence. We are looking at the hard meteorological data that's accumulated since 2006.
The real numbers.
Yes, the real numbers. We want to analyze the thermodynamic mechanisms driving current global weather anomalies and examine the evolving challenge of how scientists communicate uncertainty.
Because that's a huge part of it now.
It really is. And our objective isn't to debate political policy or engage in alarmism. We are here to impartially dissect the physics of the atmosphere, the historical precedents for solving environmental crises, and the very real data surrounding the air we breathe right now.
Establishing 2006 as a baseline gives us this really fascinating 20-year scorecard. Al Gore actually recently gave an interview marking that 20th anniversary.
Right, I saw that.
Yeah, and when you systematically review the core scientific claims presented in that original documentary against the satellite and terrestrial data we have today, the vast majority of the broad physical predictions have manifested.
They have. The observational data from NOAA and also the Copernicus Climate Change Service, it really confirms the underlying physics. I mean, the period from 2015 to 2025 represents the 11 hottest years in the instrumental record.
Wow, 11 years straight.
Yeah, we are seeing a sustained upward shift in the global mean temperature that entirely eclipses any sort of natural multi-decadal variability.
But the surface temperature is just proxy, right?
Right. The more rigorous metric is what is happening in the cryosphere, particularly the Arctic. The documentary heavily emphasized Arctic sea ice decline, and the reality is tracked really closely with the more aggressive modeling from that era.
I want to examine the ice data closely, actually, because the popular conception of, melting ice usually just involves a shrinking white polygon on a map. You see it on the news and it just looks smaller.
Just a 2D shape shrinking.
Yeah, but the true structural damage is in the loss of multi-year ice, the old ice.
Yeah, multi-year ice is the foundational architecture of the polar ice cap. When ocean water freezes, it forms first-year ice, which is it's relatively thin, salty, and fairly fragile.
Okay.
But if that ice survives the summer melt season, it undergoes a process called brine rejection. Over the winter, the salt is essentially pushed out of the ice matrix, and that makes the ice significantly harder, thicker, and much more structurally sound.
So it acts like a shield.
Pretty much. This old ice can survive turbulent ocean swells, extreme summer anomalies, things like that.
But according to the 2025 Arctic report card from NOAA, that old ice is practically gone. I mean, we've seen a decline of over 95% since the 1980s.
95%.
It's wild. So while we might have a similar surface area of ice in the dead of winter, it is overwhelmingly this fragile first-year ice. It's sort of the structural equivalent of replacing a concrete foundation with, a layer of frosted glass.
That is a really good way to put it.
The moment the sun returns in the spring, it simply shatters and melts.
And that loss drives a massive thermodynamic feedback loop through the albedo effect. Multi-year ice is highly reflective, so it bounces shortwave solar radiation back into space.
But the open ocean doesn't.
No, when you replace that ice with dark open ocean water, the ocean just absorbs that incoming solar radiation. It warms up, and that actually delays the freezing process the following autumn. This latent heat absorption is why the Arctic is warming at nearly 4 times the global average rate.
Okay, but let's look at a prediction that did not follow the modeled trajectory, because this is where the socioeconomic variables really intersect with the physics.
The carbon models.
Right. The 2006 projections suggested that global carbon dioxide concentrations could hit 500 parts per million within 50 years. So in 2006, we were sitting at roughly 380 parts per million.
Right.
Today, in 2026, we are crossing 430. Now, that is a massive increase, roughly 50% higher than the pre-industrial baseline of 280, but we are noticeably bending the curve away from that worst-case 500 trajectory.
We are.
So if the ice is melting and the heat is rising, what exactly disrupted the carbon curve?
Well, the disruption was economic. The models in 2006 heavily underestimated the Swanson effect.
Which is the solar panel pricing.
That is the core of it, yeah. It's the observation that the price of solar photovoltaic modules drops roughly 20% for every doubling of cumulative shift volume.
Wow, 20% is huge.
It really is. The sheer scale of global manufacturing, coupled with, advancements in material science and wind turbine aerodynamics, it fundamentally altered the levelized cost of energy. Renewable generation simply became cheaper than extracting and burning pulverized coal in a lot of markets.
Which brings us back to that May 2026 milestone, right? Where solar surpassed coal in the U.S. grid. It was basically an economic inevitability once the manufacturing supply chain scaled up.
Yeah.
But even with that bent curve, we still have to contend with the physical reality of 430 parts per million currently sitting in the atmosphere. In his recent interviews, Gore utilized a pretty striking analogy to quantify the radiative forcing caused by this concentration.
The atomic bomb analogy.
Yeah. He stated, we are trapping thermal energy equivalent to 800,000 Hiroshima-class atomic bombs exploding every single day.
And, that analogy sounds hyperbolic,
Mm-hmm.
but mathematically it aligns with the calculations of Earth's energy imbalance.
Okay, walk me through the math there.
Sure. The sun constantly bathes the Earth in shortwave radiation. The Earth absorbs this and then radiates it back out as long-wave infrared radiation.
Right, basic thermodynamics.
Yes. But greenhouse gases, like carbon dioxide and methane, they act as an opaque barrier to that specific infrared frequency. They prevent it from escaping into space. So when you calculate the raw wattage of that trapped energy across the entire surface area of the globe, it equals just an astronomical amount of joules.
I have to challenge the daily reality of that math, though, because, if we are genuinely trapping the equivalent of hundreds of thousands of atomic detonations of thermal energy every day, why isn't the surface of the planet entirely unlivable right now? Where is all that thermal latency actually hiding?
It is hiding in the oceans.
Oh, right. The specific heat capacity?
Yes, the specific heat capacity of water. Water requires roughly 4 times as much energy as air to raise its temperature by a single degree. Furthermore, the oceans are incredibly dense and deep. Over 90% of the excess thermal energy trapped by greenhouse gases over the last 50 years has been absorbed by the global ocean.
90%.
Yeah. If that energy had gone entirely into the atmosphere, surface temperatures would have already risen by dozens of degrees. The ocean is effectively acting as a massive thermal flywheel, absorbing the blow. But in doing so, we're seeing rising sea levels from thermal expansion and a drastic increase in the energy available for phenomena like tropical cyclones.
And the policy response to managing that carbon baseline has been, notoriously volatile. We've seen significant friction at the international level. For instance, the Trump administration temporarily withdrew the United States from the Paris Agreement.
Right.
And the rationale centered on the argument that the treaty's framework placed an undue burden on the American economy and did not align with domestic taxpayer interests. As a matter of historical record, that withdrawal just highlights the sheer friction involved in transitioning a global energy grid.
It's very complex.
Yeah, this isn't just an engineering problem. It is deeply entangled with national sovereignty, domestic economies, and political inertia.
And that economic friction forces us to look for mitigation strategies that don't rely solely on massive international treaties. This is where the concept of invisible inefficiencies becomes critical.
Invisible inefficiencies.
Yeah, in his retrospective, Gore highlighted how artificial intelligence and machine learning algorithms are now being deployed to optimize industrial power grids.
Yeah.
And they're doing it in ways human engineers simply couldn't map out.
He also pointed to municipal landfills, which I thought was fascinating. The decay of organic matter in landfills releases immense amounts of methane. And methane has a global warming potential roughly 28 times greater than carbon dioxide over a century-long timescale.
It's potent.
Really potent. And simply installing engineered covers over these landfills to capture and flare or even utilize that methane that could eliminate more greenhouse gas equivalent than the combined emissions of all global data centers.
That is a staggering comparison.
It really grounds the conversation, I think. We often frame atmospheric mitigation as this, like, futuristic, high-tech endeavor. But sometimes the most mathematically effective solution is literally just optimizing our waste management infrastructure.
And this specific point regarding targeted pragmatic solutions, it serves as a crucial transition in our understanding of environmental history. Because, there's often an inherent pessimism when looking at the multi-year ice data or the rising parts per million.
Sure.
It raises a legitimate question of whether global-scale atmospheric engineering is even feasible for human institutions to manage.
Mm.
But historically, we have empirical proof that is entirely possible.
Yeah, that historical track record is exactly why we need to examine the problems society has actually solved. The defining difference between the historical chemical bans of the 20th century and our current carbon challenge is that, well, carbon is the bedrock of the global economy, whereas past threats were often byproducts of specific niche industries.
Very true.
But the mechanics of how we solve them remain highly relevant. So let's look at the ozone hole. In 1985, the British Antarctic Survey published data showing a massive depletion of stratospheric ozone over the South Pole.
And the mechanism behind that depletion was incredibly specific. Chlorofluorocarbons, or CFCs. They were highly stable, non-toxic chemicals used heavily as refrigerants and aerosol propellants.
In, like, hairspray and refrigerators.
Right. And because they were so stable, they didn't break down in the lower atmosphere. They drifted up into the stratosphere, where intense ultraviolet radiation finally sheared off the chlorine atoms.
Okay.
Then, in the extreme cold of the Antarctic winter, polar stratospheric clouds form. These clouds provide a physical surface for the chlorine to undergo catalytic reactions. A single chlorine atom could destroy tens of thousands of ozone molecules, severely thinning the layer that protects the surface from harmful UVB radiation.
The threat was existential. I mean, without the ozone layer, life on the surface is cooked. But the geopolitical response was unprecedented. The 1987 Montreal Protocol was drafted, establishing a binding schedule to phase out CFC production.
And it remains the first and only United Nations treaty to be universally ratified by every nation on Earth.
Every single one. And the atmospheric data confirms its success.
It does. It requires patience, of course, because the atmospheric lifetime of CFCs spans many decades. But the concentration of ozone-depleting substances in the stratosphere is steadily declining. Observational data confirms the ozone layer is thickening.
That's incredible.
Yeah, and barring any new illegal manufacturing of these chemicals, the mid-latitude ozone is projected to recover to 1980 levels by around 2040, with the Antarctic hole closing by the 2060s. It is a triumph of applied atmospheric chemistry and international diplomacy.
We see a similar success story with acid rain, which, really dominated environmental science in the 1980s and 90s. The mechanism here involved sulfur dioxide and nitrogen oxides, primarily emitted by coal-fired power plants. Once in the atmosphere, these gases react with hydroxyl radicals and water vapor to form sulfuric and nitric acids.
And the meteorological challenge with acid rain was transport.
Right, it doesn't stay where it's made.
Well, yes, a power plant in the American Midwest might emit thousands of tons of sulfur dioxide. But then the prevailing westerlies would carry that for hundreds of miles before precipitating out over the forests and lakes of New England or Canada.
Lowering the pH of aquatic ecosystems.
Yes, essentially suffocating fish populations and leaching toxic aluminum from the soil right into the watershed.
The regulatory fix for this was an incredible piece of economic innovation. The 1990 amendments to the Clean Air Act, which instituted a cap-and-trade system. Rather than just fining companies or dictating exactly what machinery they had to buy, the government set a hard cap on total allowable sulfur dioxide emissions and issued allowances to power plants.
And the genius of it was the market aspect. If a facility installed flue gas desulfurization technology, commonly known as smokestack scrubbers, and dropped their emissions below their allotted cap,
They could sell their excess allowances.
yeah, they could sell them on the open market to a facility that was struggling to transition. It incentivized rapid technological adoption because reducing pollution became a direct revenue stream.
The data from the EPA validates this market-based approach completely. Since those regulations took effect, sulfur dioxide emissions in the U.S. have plummeted by 95%.
95%.
Nitrogen oxides are down 89%. We effectively scrubbed the troposphere of a massive chemical threat, and the underlying economy actually grew during the process. We didn't have to shut down the grid to clean the air.
And this capacity for self-correction extends into the biosphere as well.
Right.
The regulation of the insecticide DDT, following the publication of Rachel Carson's Silent Spring in 1962, is a prime example.
Right.
DDT was a remarkably effective tool for combating malaria and typhus during World War II, but its post-war agricultural application was, well, indiscriminate.
The core issue is that DDT is highly lipophilic. It stores itself in the fat tissues of animals, and it strongly resists environmental degradation. This leads to biomagnification.
Yes, up the food chain.
Right. An insect ingests a microscopic amount, a small bird eats hundreds of those insects, and an apex predator, like the bald eagle, eats the birds. At each trophic level, the concentration of the chemical magnifies.
In raptors, the accumulated DDT and its metabolite DDE fundamentally disrupted the calcium ATPase enzyme in the shell gland. This meant the birds could not properly calcify their eggs. The shells were so thin that the normal weight of the incubating parent would crush them.
Just sitting on them.
Yes. By 1963, the bald eagle population in the contiguous United States had crashed to just 417 known nesting pairs.
Just over 400. That's so low. But then the EPA formally banned the agricultural use of DDT in 1972. Removing that persistent chemical from the food web allowed the calcium metabolism of these apex predators to normalize. Today, the population has rebounded to over 70,000 nesting pairs.
It's a massive recovery. When we look at the ozone hole, acid rain, and DDT, the unified takeaway is empirical proof of societal capability. The scientific method correctly identified the mechanisms of destruction, communicators effectively translated that risk to the public, and policymakers deployed regulatory frameworks that worked. We have the institutional architecture required to solve atmospheric crises.
But that architecture is being severely stress-tested today. The defining difference right now is that the thermal energy trapped by carbon dioxide is fundamentally rewiring how human beings gather, worship, and compete. It is no longer a localized chemical threat. It is a systemic redistribution of planetary heat. We can see this vividly when we analyze the specific meteorological impacts on global events.
Like the logistics of the 2026 FIFA World Cup.
Exactly. The 2026 World Cup presents a highly complex logistical challenge because it is distributed across the United States, Canada, and Mexico during June and July. You are taking elite athletic competition and overlaying it onto a massive geographic footprint during the peak of the Northern Hemisphere's solar insolation.
And to understand the genuine physiological threat to the players and the fans, we have to look past the standard dry bulb air temperature. The critical metric is the wet bulb globe temperature, or WBGT.
Okay, let's break that down for the listener.
The human body is essentially an internal combustion engine that needs to vent heat. When you are exercising in a dry desert, even if it is 95 degrees Fahrenheit, your sweat evaporates almost instantly. That phase change of water from liquid to vapor physically pulls thermal energy away from your skin.
That process relies on a vapor pressure deficit. The dry air has the capacity to accept the moisture, but if you place that same athlete in a highly humid environment, say 90 degrees Fahrenheit with 85% relative humidity, the ambient air is already nearly saturated.
Right. The vapor pressure gradient collapses. The sweat simply drips off the body without evaporating, meaning the evaporative cooling mechanism fails completely. The internal core temperature begins to rise unchecked, leading to heat exhaustion or fetal exertional heat stroke.
WBGT quantifies this exact thermal strain. It isn't just humidity. It incorporates radiant heat from the sun, the ambient air temperature, and the cooling effect of ambient wind. It is a holistic measurement of physiological stress.
And FIFPro, the Global Union for Professional Football Players, relies on strict WBGT guidelines. When the WBGT hits 26 degrees Celsius, matches require mandatory cooling breaks. If the WBGT reaches 28 degrees Celsius, the conditions are deemed hazardous, and postponement is strongly recommended.
The modern attribution data modeling for this tournament is highly concerning. Researchers mapped the climatological baselines of 1994, the last time the U.S. hosted the World Cup, against the baselines for 2026. The probability of exceeding those 26 and 28-degree WBGT thresholds during afternoon matches has increased significantly.
The thermal load on the human body is tangibly higher now, and this extends far beyond the pitch. While stadiums can be air-conditioned, the hundreds of thousands of fans navigating public transit, waiting in security queues, and attending outdoor viewing parties, they're exposed to a heightened level of physiological risk.
We see an even more extreme intersection of meteorology and human congregation with the Hajj pilgrimage in Mecca. This is one of the foundational pillars of Islam, involving roughly 2 million people gathering in a highly concentrated area.
2 million people.
Yeah, and the physical demands are intense. Pilgrims spend 20 to 30 hours outdoors, often walking long distances, shoulder to shoulder, with incredible crowd density.
The climatological complication here is driven by orbital mechanics and the Islamic lunar calendar. Because a lunar year is roughly 11 days shorter than the solar year, the dates of the Hajj continuously shift backward through the seasons. Currently, the pilgrimage is falling in the month of May.
Historically, May on the Arabian Peninsula was considered a transitional, relatively safe month before the establishment of the intense summer subtropical ridge. The brutal, life-threatening heat typically peaked in June, July, and August.
But the shifting baseline has essentially erased that buffer zone. The observational data from the region confirms a severe escalation. Daily average temperatures in Mecca during May are now hitting 31.2 degrees Celsius.
That's the average.
Yes. To understand the magnitude of that shift, May is currently experiencing the identical thermal profile that the peak summer months experienced in the 1970s. The season of extreme heat has expanded geographically and temporally, pushing backward into the spring.
The research indicates that daily maximums crossing 40 degrees Celsius over 104 degrees Fahrenheit, which used to be rare anomalies in May, are now statistically expected every 2 to 3 years.
It's becoming the norm.
Right. And the Saudi authorities have engineered massive mitigation efforts. They've installed extensive misting systems, reflective paving, and vast shading structures. But at a certain point, the physics of wet bulb temperatures and massive crowd density begin to brush against the absolute thermodynamic limits of human survival.
This expansion of the extreme heat season is highly evident when we look at the pre-monsoon period in South Asia. Throughout April and May, regions across India and Pakistan have recently recorded daily highs exceeding 46 degrees Celsius.
And we're 114 Fahrenheit.
Yeah, but the meteorology of the Indian subcontinent presents a deeply complex and dangerous paradox regarding how this heat manifests.
This is where atmospheric chemistry and human agriculture collide in unexpected ways. If you look purely at the increase in maximum dry bulb temperatures over South Asia, it actually appears slightly lower than the global average warming trend. But the lethality of the heat waves has skyrocketed.
It seems like a contradiction.
I would think that if anything is masking the heat, it would be a benefit. If the dry bulb temperature isn't rising as aggressively as other regions, why is the health risk so much higher?
It seems counterintuitive until you examine the variables masking that heat. The primary factors are high concentrations of atmospheric aerosol pollution and a massive decadal increase in agricultural irrigation.
How do those interact?
Well, the sulfate aerosols and the pollution physically scatter incoming shortwave solar radiation, bouncing it back into space before it can heat the surface. Simultaneously, the vast irrigation networks provide surface water that evaporates, utilizing thermal energy for a phase change rather than raising the ambient air temperature.
But that evaporation is a trap. The latent heat flux is pouring millions of tons of water vapor into the boundary layer.
Yes, they are trading dry bulb heat for wet bulb heat. The air might register a degree cooler on a standard thermometer due to the aerosols and evaporation, but the relative humidity is massively artificially inflated.
Wow.
And as we discussed with the World Cup, high wet bulb temperatures neutralize the human body's ability to sweat. A 15-day heat wave combining these specific parameters is now modeled to be 3 times more likely than in a pre-industrial climate. The masking effect of the pollution is actively making the physiological conditions more deadly by trapping the population in a hyperhumid atmospheric dome.
That redistribution of thermal energy is forcing us to rethink our assumptions about every region on Earth, even the most isolated ones. Which leads us to the data out of Antarctica from June of 2026.
The events documented on the Antarctic Peninsula during that month represent a profound climatological anomaly.
To set the baseline, June is the absolute dead of winter in the southern hemisphere. The Antarctic continent is tilted away from the sun, plunged into continuous darkness, and locked in a deep, sub-zero freeze. Yet, at Argentina's Esperanza base, researchers recorded a temperature of 15.4 degrees Celsius.
That is over 60 degrees Fahrenheit.
Let that sink in. 60 degrees in the middle of the Antarctic winter.
Climatologists analyzing the data noted that this single event represented a temperature anomaly of roughly 20 degrees Celsius above the historical norm for that location and time of year. It shattered previous winter records at that station by a full 2 degrees.
And the physical impact on the ice was immediate. Glaciologists surveying the Collins Glacier reported rain, not snow, but liquid rain falling on a glacier during the polar night.
Which is unprecedented.
Right. Normally, winter is when these ice sheets accumulate mass through snowfall, rebuilding what they lost during the summer. Instead, you have liquid water falling on the ice, releasing latent heat as it freezes, or simply washing away the surface layer.
The atmospheric dynamics driving this event are tied to the behavior of the westerlies. We are observing an increase in the frequency and intensity of atmospheric rivers, narrow corridors of concentrated moisture in the atmosphere, penetrating the circumpolar vortex.
Okay, so the moisture gets driven south.
Yes, and when these systems impact the topography of the Antarctic Peninsula, they generate foam winds. As the air is forced over the mountains and descends on the other side, it compresses and warms adiabatically. That leads to these intense, localized temperature spikes.
Well, a single warm week won't melt the entire ice sheet. It exposes the structural vulnerability. Scientists are monitoring the marine ice sheet instability of massive formations like the Thwaites and Pine Island glaciers.
The buttressing ice shelves.
Right. If the buttressing ice shelves that hold those terrestrial glaciers back are weakened by anomalous winter rain and warming ocean currents, they could unpin from the bedrock. That crosses a tipping point where you move from millimeters of sea level rise to potentially meters over the coming centuries.
It is an interconnected fluid dynamic system. The latent heat flux over India, the shifting westerlies over Antarctica, the expanding subtropical ridge over the Arabian Peninsula. These are all symptoms of an atmosphere working to redistribute an excess of thermal energy. And understanding these highly complex interwoven mechanisms requires an evolution in how we process and communicate the data.
The gap between the physical realities of the atmosphere and the public's understanding of those realities is arguably the most critical friction point in modern meteorology. 20 years ago, communicating this science often meant pointing to supercomputer models predicting generalized global conditions for the year 2050 or 2100. It felt abstract. Today, the frontier of communication is attribution science.
Attribution science has effectively bridged the gap between long-term climatology and daily meteorology. Organizations like World Weather Attribution utilize a methodology called the fraction of attributable risk. They don't just forecast the future, they forensically analyze the present.
Like a post-mortem for a weather event.
Essentially, yes. When an extreme event occurs, like the South Asia heat wave, they run massive ensemble models of the event under current atmospheric conditions.
And then they run a counterfactual model. They simulate the exact same synoptic weather pattern, but they strip out the excess greenhouse gases added to the atmosphere since the Industrial Revolution.
Exactly. By comparing the factual world to the counterfactual world, they can statistically quantify the impact of the warming baseline. They can state with mathematical confidence whether a specific heat wave was made twice as likely, or 10 times as likely, or physically impossible without the elevated carbon baseline.
But this precision carries an immense burden of responsibility. As meteorologists, having access to attribution data doesn't mean every single thunderstorm or dry spell is entirely driven by a shifting climate. Natural variability phenomena like an El Niño or La Niña still fundamentally drive the daily weather.
Right, the background noise is still there.
Right. If a communicator overhypes a single event, they degrade the public trust required to communicate the actual systemic risks.
This is why the approach taken by science communicators like meteorologist Daniel Swain is so vital. The objective is to communicate probability density functions rather than relying on deterministic alarmism.
Shifting the curve.
Yes. A trusted meteorologist explains how the baseline is shifted, moving the bell curve of probability so that the extremes become more frequent. They must clearly delineate what is known, what is modeled, and where the margins of uncertainty lie.
That requirement for absolute epistemological rigor brings us to a rapidly emerging threat that could undermine everything we've just discussed. The entire framework of attribution science relies on the integrity of the peer-reviewed data. But a new variable is entering the ecosystem: AI-generated fake scientific journals.
This is a huge issue. The scientific community is currently grappling with the proliferation of paper mills. These are operations that use large language models to generate plausible but entirely fabricated scientific papers.
It's terrifying.
In the realm of meteorology and climatology, these models can hallucinate complex correlation matrices between localized weather phenomena and broader global teleconnections. They produce graphs, data sets, and citations that, at first glance, appear highly credible.
This creates an epistemological crisis. The bedrock of scientific consensus isn't built on single papers. It's built on meta-analyses and systematic reviews that aggregate hundreds of studies.
Yes, the aggregate data.
If the digital archives are flooded with AI-hallucinated data, it poisons the well. How does a researcher in 2030 run a meta-analysis on Indian agricultural evaporation rates if 20% of the underlying literature was generated by a language model optimized to mimic scientific syntax rather than reflect physical reality?
It forces the scientific community to develop new forensic tools just to verify the provenance of the data before they can even begin to analyze the physics. Ensuring the integrity of the scientific literature against AI pollution is rapidly becoming as critical to meteorology as maintaining our satellite arrays.
It's an intimidating landscape when you layer the complexity of wet bulb thermodynamics, shifting global atmospheric patterns, and now the contamination of the data itself. But we have to return to the overarching theme of the last 20 years. Science is a fundamentally self-correcting process.
It is.
It isn't perfect, but it is resilient. We identified the ozone hole, understood the chemistry, and implemented a fix. We recognized the devastation of acid rain and DDT, utilized market mechanics and regulation, and allowed the ecosystems to recover.
The data we gather, no matter how daunting, is ultimately a tool for adaptation. Because we understand the exact physiological limits of WBGT, organizations can mandate cooling breaks at a World Cup. Because we have precise thermal modeling for the Hajj, authorities can deploy targeted misting infrastructure.
Right.
Because we have mapped the economic efficiency of solar power, the grid is actively transitioning. The attribution data and the climate models are not designed to induce paralysis. They are the blueprints required to engineer our survival.
I want to leave you with a final thought to mull over. As our attribution models and localized forecasting become increasingly hyper-accurate, we're approaching a reality where the ambiguity of the future climate is erased. We will soon be able to predict the specific climatic conditions, the exact number of unsafe WBGT days, and the flooding probabilities of a specific zip code a decade in advance.
Down to the neighborhood level.
Yeah. When the future of your neighborhood's weather is no longer a generalized guess but a mathematical certainty, how will that alter our culture? If you knew exactly what the atmosphere would demand of your city in 10 years, would you change where you live, or would you radically change how you build your community? When the data is undeniable, the weather stops being just a science problem and becomes the defining human problem. Well, if you want to keep exploring the science behind the weather, make sure to follow Rob Jones on Instagram, TikTok, YouTube, and Facebook. And please take a second to like, follow, comment, and rate the podcast. It really helps us out.
We appreciate you taking the time to examine the data and the mechanisms with us today.
You've been listening to Meteorology Matters, created by meteorologist Rob Jones. Thanks for listening, and remember, meteorology always matters.